Okay, well, start.
Okay. So first, just wanted to make sure that we are aligned in the notation terminology we are using. So I wanted to start by telling you what I consider to be a quantum state. For me, a quantum state is just a representation of a quantum system, and mathematically it can be described as the probability distribution of the outcomes, of the different outcomes. Okay, so in general, in quantum information theory, we deal with two different types of states. We have what is called the pure states and mixed states. Probably everybody will something that you may know, but just to make sure. Okay, so pure states are basically what you already know. They are vectors in a certain bigger space. And mixed states, for me, are just positive definite numbers. Okay, so we have a vector here, it will verify these conditions. In particular, for in the given space. Okay, we want to focus on this. Maybe. We usually express these vectors using this notation. So you probably know that the Latin notation using the brackets. Yeah. Basically, I'm going to be using the arc notation, but I will refer to the vectors in the Hilbert space. So normally, when you're considering vectors in the Hilbert space, one thing that bothers us a lot is the dimension of the space. So normally, if you assume that we are dealing with a Heisenberg model system with n particles, then the dimension scales exponentially with respect to the number of particles, which is not quite good if you want to explore the whole space. So if you have the whole bigger space, it's quite big, but in quantum information theory, we found out that there are some vectors within this space that are more interesting than others, and we call them the exceptional set. And these are vectors that are really interesting. Maybe you're wondering, okay, which ones? These ones are the ones that verify what is called the area. Okay? So the area law is basically just a way of interpreting a physical property, which basically tells you that states should be correlated in a local manner. So they tend to be correlated due to a local behavior in the system. Okay, I can dive deep into this. Basically, if you take the whole space and you have here a certain, and you take some of the vectors in the area, then this will verify that you can somehow upper bound the entropy of the system in that area. That's the interesting part of the area law. We can dive deep into that if you want. But just to move on, basically you're dealing with this exceptional set which contains these vectors that follows the area line. I have listed some of the properties of the physical systems and physical Hamiltonians and everything that you might be interested in that follows this so-called area law. So for example, and these are just things from the physics side. But this is who follows this area law. All the ground states, which are from gap models. This means how many domains and all the things. As Mikael told you, don't ask me what a Hamiltonian is because I don't know. Eigenstates of models with the graphs. These are well represented by these vectors. Well, thermal states, which is non-zero.
So can I ask you, what's the second point? Eigenstates of what?
Eigenstates of models from mobility graphs. With mobility graphs.
And I have another question. I didn't get the area law, so it's the area of X is bigger than S of.
Okay, I can dive into that. So the idea is to calculate this entropy, which is not. Okay. So there are different types of entropy. In particular, for this case, we are using what is called the minimum entropy. Okay. Probably you guys know more about this.
I mean, it simply seems that the entropy scales with the area.
Yeah,
The boundary between the two.
but the idea
The
is.
boundary the volume.
But it's the area of what?
The area, the boundary between the two.
Okay, this is the whole
If you have a partition, if you have a big system, you have to.
Okay.
Basically, you want all the vectors to verify that if you take the entropy of the system of the bounded region, you can upper bound that that value of entropy.
Okay.
But we're using the volume of entropy. We can talk offline after this about this. Just for the sake of minimum, I'm trying to reach to the tensor network. This is just some context of why are we doing this. So these are some interesting applications of these states. And then one thing that maybe you should ask yourself once you have reached this point is, okay, so we already know that there are a huge amount of vectors. We all know that there is an exceptional set of vectors that we are interested in. How can we express those vectors efficiently? Or how can we express those vectors in a way that it's easy to manage, to handle them, to work with them? This is where tensor network came from. So the first idea was, okay, so we know that these states can be bounded in a certain subset of all of the vectors in the Hilbert space. How can we represent it? Someone came up with this idea of multiplying matrices and then creating what is called the MPS family. But before we start with that, I want to briefly introduce you to the notation we are going to use. So basically, a tensor, this is just a context we are going to be using later. A tensor is just a collection of elements I'm sorry for the scratchy sound. Okay, so given a vector space, a tensor is just a collection of elements, a multidimensional collection of elements. I'm going to call it A, for example, and then we will have some indices. Each of the indices represents the dimensions that the tensor is living on. Okay, and we can, in particular, we can call this N as the rank of the tensor. So for example, sorry. So, for example, some examples of tensors that you already know. I'm scalar, let's say, I'm scalar. This is a tensor of rank 0. and you have a matrix. For example, two. Your matrix. The value of this matrix is 2. And you can go and have different tensors of higher dimensions and higher ranks. Okay? So you have the idea more or less of what a tensor is. It's just a fancy name of telling we are grouping elements somehow. It's also a way of telling you this is a multidimensional map, because as you probably know, a matrix is just a linear map application, and if you go to higher dimensions, you're creating also more applications. Indeed, those are also applications, but just restricted to lower dimensional spaces. Okay, so once you figure out that this is these are all tensors, we are interested in working with these tensors. So we have a really cool tool, which is called the contraction, which allows you to work with this tensor using the indices. So imagine you have this really common operation. You have A, B, and B. You take two matrices and you want to multiply them. So you normally just take the row and then start operating with the whole algorithm of taking the row, multiplying by the column, adding numbers. You keep doing that. In tensor network theory, what we do is we identify the indices that are common, and this means that we are adding over that index. So, for example, the result of these two matrices could be expressed as this. Which means that we are basically identifying the G index of both tensors so that they are joined together. Okay? And this is just matrix multiplication. But we can do cooler things. So now you have this tensor, we can identify itself, but we can identify it with itself just by identifying the E index with the E line index. So here we identify these two. Here we can identify this one. So while we're doing here, we are calculating the layers. Okay? So you can start doing cool things with this. Okay. For MPS, which were the cool quantum states that I told you about that can be represented using these tensors, you can actually represent them mathematically using these expressions, and they can be expressed that way. But most of the tensors that we deal with are quite huge. And if you start, for example, joining indices, imagine that you have a huge vector with a lot of indices, and you want to join it with another one with, I don't know, a lot of indices. And then you will start having problems. This will lead you to a lot of things, and you have to start somehow fixing them and doing contractions. We don't want that. We don't want this because you cannot work with these expressions. They're quite opaque. So people from the quantum information theory decided that it would be really cool to have a diagram representation of these things. Okay, so I'm going to introduce you to the diagram representation. Here we have this scalar, which is a tensor of rank 0. We will draw just a circle. Okay, if we have a tensor of rank 1, we will have a circle with a line. And then for tensor with rank 2, we will have a circle with 2 lines. And then we will keep adding lines for each of the dimensions that we are adding. So for each index, we will have another arrow. And then how does this work with the idea of contraction? So it's a direct mapping. When we start contracting, we are just joining together the lines. So for example here, this same operation can be represented by this connection. And then this is also equivalent to having another tensor. So apparently we have two things now. So we can now start drawing diagrams that are more beautiful than these equations, and they can be easily managed. And also we have to figure out something. When we start joining tensors, we are also finding another tensors. So this idea of generating tensors using tensors is what lately will be eventually lead us to the idea of families of tensors.
What if you connect a tensor of order 0 with a tensor of order 1?
You cannot.
Okay.
There are no lines. Okay.
So you cannot define a multiplication of the scalars in that sense.
Well, you can work around a way of drawing that. The purpose of having this line, okay, if you want to dive deep into this, this is just a simplification of the way they are going to be presented. In reality, you will also require to have arrows indicating the sense of the direction you are moving on. Because as you told me, sometimes you want to multiply by a scalar, or sometimes you want to transpose or calculate the complex conjugate or something. In that sense, we are, with this diagram notation, we are lacking some tooling. But I think it's easier to just restrict ourselves to having the contraction operation for elements of the same dimension, or at least elements that share a common dimension. Because this way, you can do things more easily. In reality, in quantum information theory, you can actually multiply by scalars, and you should also provide the direction when doing this. But then you will have to define this not as a vector, but as a vector or a vector from the dual space, and then you will have to be dealing with more things, which we can do it, but I think it will be more cumbersome for us. Probably we'll spend a lot of time explaining this. For example, here, you cannot join this with another index, even if they match in dimensions, and that's why this is not the direction of both indices are different. One is from the dual space, and the other one is from the vector space. But let's not dive deep into that. You can do it, not with this notation I introduced you to. But you can do it in theory, so this can be generalized.
Yeah. I thought that you could connect a tensor of order 2 resulting into that notation into one of order 1. You multiply
this code, you can connect it.
Yeah. Okay, but
this is multiplying just by the matrix by the vector. But then, for example, here, okay.
But you can.
I told you about the arrows and the direction is because if you have this, what is the meaning of this? It's multiplying by the left or by the right the matrix. So this means this is not the vector, this is actually this one. But because if this is oriented this way, which is the normal way, you just have. Okay. So the idea of what I'm talking about is this. Why are they different?
Dual and normal space.
What? They have one
One is the
space.
dual and
One is from the dual space, and the other one is living in the inverse. And that's an issue because if we start messing around with these things, we will need to define a direction of the arrows, and then you can only join the ones that match in the direction in the sense that one is the dual space and the other one is the vector space. But let's not move to this. I prefer just to restrict ourselves to this notation. We can just join things that match in the direction, and we are not worried about if we are living in the dual space or if we are living in the vector space. You can do it. We are not doing it now. Okay. Okay. So, for example, here, how do you calculate the trace? Any ideas? How these contractions will work in the diagram?
You said, I would think you can join the two ends, but I think you said it's not.
Yeah, you can do it.
Okay.
Here we go. So this is calculating the trace. Okay? So this is just really basic tensor representation presentation in terms of theory, but it's the basic foundation you need to understand what MPMs are and what waves are. There are more things, as I told you, and you should also worry about the direction of the arrows and more things, but let's simplify things. Okay. I have here an example that maybe might be interesting. So, as I told you, this is quite cool because if you have, for example, let's say, this thing is quite easy to draw, but it's quite hard to express. Even if I start doing crazy things like, for example, doing things, this can get quite messy. So that's why we are using this diagram notation. And it's more intuitive, you can walk around properties around these structures, and it's quite cool. Okay, so what are MPS? I'm going to provide you both the mathematical formula as well as the diagram. I prefer to start with the diagram. We have two types of MPS, but MPS are basically just a family of states that are generated using these structures. And they are really useful because they can be used to actually generate the states efficiently. In particular, every finally correlated state can be generated efficiently using MPS.
What does MPS mean?
Oh, yeah, sorry. This is finally from the state. You will see now why the name, why this is the name of this thing. So basically, using the diagram, and MPMs looks like you can have a lot of matrix multiplication, and then you will use this open. This is called an MPM with open conditions, but we mostly are interested in this one. Okay? Then you have your vector. How do you represent this mathematically? Anyone want to give a try? What's the meaning of this using formulas? Basically, this is a vector, but what is?
It's a partial trace.
It's a
Partial trace.
It's a partial trace. It's the sum of okay, as you can see, it's not that good. I do prefer the diagram expression. You can express this using mathematical formula. Basically, you're just telling us, okay, you're calculating the rates of this product, and you have to take into account all the different indices. Okay. So you can see this is getting quite complex, and this is just one of the most simple families we have. Indeed, now we have the definition of what an MPS is. I can show you what vectors are. So this is projective, entangled, wave states. Okay. And this I'm going to draw the diagram, but I'm not stating the formula. Well, I can state the formula, but we are not doing it. The idea is mostly the same, but instead of joining things in one dimension, we will be joining things in gonna be a lot messy.
In the state side A that we wrote there are some indexes which were left unconnected. Doesn't mean that there should be an index that is not summed over.
Well,
On the side A state and the
Here?
drawing. Yeah, that and the drawing. There are some lines that were unconnected.
That
So that
means
means that some indexes shouldn't be summed over, right?
what?
That means that some indexes shouldn't be summed over, right?
Shouldn't what?
That means that some indexes shouldn't be summed over.
Oh, you should not. Yeah. I'm doing just the ones that are here.
Okay, so there are some hidden indexes.
Yeah, the vector one. So I giving a relation for the vector.
So the
Yeah.
I is a set of matrices. It does not really
Yeah.
know the index of the matrix. It is each matrix you are using.
So yeah. So these are the small ones.
So maybe in the drawing you can write where the I1, I10 is.
Oh, so these are just
So it's
these are matrices including D times D matrices. Let's say.
But if you have three lines, it's not a matrix, it's a...
That's why I'm leaving having index open.
okay.
So I need an index open for the vector step.
What I mean is that in the not contracted indexes, in the drawing.
Sorry, it's really difficult to hear you with the mask.
Yeah, I think of this one is corridor. I mean that the indexes that you are not contracting in the broad path correspond to I1, I2, I3, IN. These are this is notation.
okay.
Uh,
The three lines.
So then-
So the state.
So you're not missing.
Oh.
It's the matrix corridor. So this one here, I1, I2, I3.
Yeah.
Okay, so that's not side A, right? It's like the set of all the individual which you are then summing over, right?
No, this is the vector. This is vector. R3.
So
The
in
one
this
that-
case, the A doesn't need the
If you give this sum, we can work through an example. Maybe it's better.
Okay.
I think that this is that this AI something, this I something is the spot of the matrix, and not the indices of the matrix.
Yeah. It normally it's easier if you write it after the never part of the matrix.
We will go through an example. Maybe it's better. Okay, let's assume we have this thing. Okay. We want to calculate the state assuming this is an MPS. So we want to calculate this. Let's say this is something like that. Okay, we want to calculate the state. How do we do it? So we are going to sum over of this. I'm going to state the full expression here. So what do we have here? So we have the trace of the product of the matrices. This means that we're going to be taking a look at this. Right? Then we're going to add the second term. This is going to be this one. Okay? And then so on. Who wants to calculate this?
Yeah, 0, 0 plus 1, 1, right? But could you draw the associative diagram of this operation?
Let's better the diagram than the full
But
version.
why you have two lines?
What?
You have two lines, this is a tensor and this is a matrix, no?
This is a vector, a huge vector.
But we said a vector has only one dimension.
Yeah, I'm somehow tricking you here because as you see here, we already merged the
Maybe
street.
it's better if you write it. several years of experience trying to explain this to everybody. So here, this tensor is you want alpha, beta, and here you have alpha, beta, and alpha.
Okay.
This is the I corresponds to the 0 and 1 that is right in here, and the alpha and beta corresponds to every element of them. So it's a three-leg tensor.
Okay. I mean, it's you have like one extra
One
which
is
is
physical. This is called the physical index because it corresponds to the real qubit of spin that you have here.
Okay.
And these ones are the bond, the virtual dimensions, which corresponds to the dimension of the matrix. Like with this, you write this way, Arturo, it's much easier to understand which part of the
Okay, sorry, I just wanted to look it simple. Probably didn't help. So, okay, are we aligned with this?
Yeah.
Here we ended up with this state, which you probably already know, not the state because that's not a functional state, but it might look familiar to most of you. We can transform that into a quantum state, yes, but not. But what is interesting here is that, okay, we use these matrices and we obtain that state. The thing is that if you try to use all the, for example, okay. You try to use those two ones, we'll have another constant which is indeed the same one. But when you say these things in mathematics, you start wondering, what the hell? So we had two different matrices and they're quite different, you can tell. And they somehow ended up generating the same state, right? So when you reach this point, you start wondering, how can I somehow prove that they are related? Sorry. You start wondering, how are these matrices related? So A and B should be, the tensor should be related in some sense, right? And that's a quite interesting question, not just because of the mathematical interest that, but also because of the physical implication that it could have. Because we are generating states, we normalize this. You will end up with a beautiful state that you're all already know. So the thing is that these two matrices, A0 and A0, A0 and B0, are indeed related, and you can get one from the other by unitary transformation, and the same applies to this two. Maybe you're wondering which H matrix is doing this thing, and surprise, because it's the beautiful Harman matrix. Okay.
We are using the notation of the star for the result.
What do you prefer?
The physical one.
The physical.
Yeah, exactly.
This thing. I don't like that because as you can tell, I'm not a good drawer, so it looks like a T. But
In this case, doesn't matter.
Okay, that's a tagger.
Yeah, that's right.
Okay. So this beautiful matrix, they start from the one tensor to the other one. And it's interesting because here using unitary transformations, we are ended up with different setups that can lead us to different to the same thing.
Yes, one question. Have you defined that psi A as all possible trace combinations of A0 and A1? Is that a definition?
The what?
That definition, psi A equals that to the sum of traces of those states.
No. This is the MPS.
Okay,
This
so
is the thing I put the summary of all the traces. This is what I meant.
so from now on, that psi A state means the sum of all traces of.
Yeah, this means the MPS generated by
Okay.
for this particular case.
But if you have defined A as a list of matrices,
This was just to make sure that you got the data as A is this huge thing.
so I guess that the representation you have used of using a lot of circles and then grouping them and having the legs out, really the way you have defined it is just a circle with one loop and one free leg, and the free leg is
You can map that to the big circle.
yeah, because the result is a vector, so in the
Yeah.
whole thing you only
You can
are
map,
allowed to have one leg.
you can map it to a big ball with a closed loop and then the line. You can map it.
So really you didn't have like a free index, but a fixed index. So this leg is the leg 1, this is the leg 2, this is the leg. No?
So, I don't think I get it.
So the thing is that if A is already a tensor of rank 3, then if you
It's
group,
not. It's not. Well, depends. What do you mean?
so A is the list of A0 and A1. So you can go in that dimension and then in the dimension inside, so you have a tensor of.
I think when you wrote there, you have to move, that you wrote A equal to A0 and 1. Yes, you have to erase it.
Oh,
you wrote here, yeah, A equal to A0, A1. What is saying is that the A itself is a tensor of rank 3.
Yeah. It is. It's a huge, big tensor. So you can map. So that's one of the cool things of MPS. For example, if you have a tensor, let's say with 9 indices, you can map this using pure mapping to a smaller tensor or to a smaller family of tensors, like let's say and you can just start playing around and build the whole thing. Just making sure that the indices matches. But by the way, using diagrams, if you have, for example, this thing, you can map it to another structure like this. I'm just making this up, by the way. You can map this around.
So this map, it means that in the map you have made with a lot of tensor, you need the same amount of free legs in one side and the other.
Exactly. Yeah.
So then the first drawing you made in which you have many circles and then one loop, that doesn't represent a...
That's a family. That's the whole family.
Okay, a family.
But
Okay, okay. Now I understand.
are we good? So the idea is that you can use this MPS to represent efficiently things. Yeah, that's mostly. I don't know if you want to dive deep into anything. I wanted to mention that indeed for MPS, this interesting feature is shared by a lot of states and by a lot of MPS by fact. So the idea is that you sometimes can find this unitary relationship between the tensors. Whenever you can find it, we say that the fundamental theorem applies. To apply the fundamental theory, it should be under certain conditions. And these conditions are related to injectivity and a lot of things. And I'm like to want to go deep into that, or we can move to divine unity theory.
But you have been interested here. Which is the relation?
Oh, yeah.
This is the relation to MPS are.
Okay, so this will lead us to eventually thinking, when can I find this relationship? And this relation can be found whenever you have an injective MPS. So we can define what an injective MPS is. And basically, you have these things here. You want to find, you want this application which takes MPS, not MPS, which is operators, and then maps them to the MPS. You want this function to be injective, and wherever this function is injective, you have to definitely can be used for the fundamental theory of MPS. I don't know if we want to go to that.
I mean, you can say
rabbit hole.
Yeah, can I ask a question? So, if for example, I have a system, and you tell me, okay, you can approximate the states in which it generally is found with an MPS, then how do I go with? So, what are those tensors?
thank you, Carlos. I was
This tensor.
for this question in the very.
Which tensors? This one.
Yeah, so what's that?
That's our matrices.
I can see that. No, I mean, you give me a physical system, you tell me, okay, you can describe it with MPS, so then you can use tensor networks. Instead, I ask you, okay, what do you do?
They are used mostly in numerical simulations. I'm not much into the details of that. I know Nico has worked with this in the past. I haven't. But as far as I know, they are used mostly to simulate and do calculations. So they can, indeed, if you go just to the ground states, for PET, for example, this is true.
No, this is not asking that. It's asking if I give you a quantum state,
Okay.
in the usual way, how do you write MPS? How do you construct it?
How do you construct the MPS from a quantum state?
Yeah, for
Okay, there are several strategies. Yesterday I was talking with Miguel about this. Indeed, I was researching on that today because it's quite interesting topic for you mostly. But there are several ways, and there are several strategies to break down the big matrix you end up with the system. If you have like a state, you can calculate the matrix with the state, and then you can break down that matrix into the products of matrices. I haven't worked myself through the whole calculation, so I'm not going to tell you because I don't know. But we can go after this meeting and check that.
Do all the matrices in which you decompose a state have rank 1?
These ones,
Yeah,
the rank of the matrices.
yeah.
The rank of the matrices according to the vector space, or the rank of the matrices according to the tensor rank is 2, but the rank of the matrices, of course, is 1.
Yeah, but if you have
They should be the same.
If you have a larger a larger state, would be the rank all the time 1.
No.
No, but they could
So
be different.
when you can diagonalize these functions, these matrices, are they always diagonal or you can get a Jordan form?
What do you mean?
You told that you could diagonalize, you can transform the representation in the matrix product state through unitary operations.
Yeah.
So if you have a representation, you can diagonalize it or at least obtain the Jordan form. So are all the matrices diagonalizable or you are going to find the Jordan form sometimes?
I'm not sure about that.
It's not the Jordan form. It's a
You can always
representation. It's a representation of this. It's a matrix by boxes, but it's not the Jordan.
So what
It's a little bit more complicated than this.
What?
It's a little bit more complicated than the Jordan.
I don't know. So
So
I guess yes, right? If you
yeah, you can do it by
you should, but I'm not sure. You should.
So I mean, if
You should be able to obtain the form for all of them.
yeah, if you have a general matrix of any rank, you can always diagonalize it or apply the
No. We cannot always diagonalize it. Depends on
or at least obtain the Jordan form of the matrix.
I don't know about the Jordan form.
So my question is if all the matrices that you are going to use to represent the matrix product state are diagonalizable, or some of them you are going to
They
obtain the
don't have to follow a certain property, so I guess no. Because you can use them. You can use.
You have many matrices. The one here tells you that 1 minute can always be written by variables into the transform, but not several of them at the same time. Is what I'm telling you.
Okay.
You can transform it into a matrix by boxes. That's not in your transform.
Okay.
So you can write. Now if you have a big matrix, the whole dimension is large. You can transform it into this. Into something like that. So you have big matrices like this one that you don't see anything, and then you can transform it by matrices by boxes. And this is a representation of the system article.
Okay. And that's supposed to be the optimal representation.
This is the canonical representation. This is the easiest one. It has a couple. And answering your question before, any state can be written as a matrix.
Yeah, but the thing is
Exactly.
okay. But the thing is how, and the how is
The
somehow
how.
tricky.
It's very, no, it's not so tricky. For this is not so tricky. So actually, when you compare the quantum state, you write it as Arturo was doing before. This is the United States. And this, with this notation, this state is nothing but something like this.
In that case, yes.
In this case, yes. So this is a general mistake for any part. The way to write this in this way is by using the singular value composition. So you apply the singular value composition here for one of the letters, and then this is a matrix. You treat this one as a matrix and this one as a matrix, and then this part can be transformed into this one.
Yeah.
And you repeat it. The optimal approach for doing this is now applying it here, and then because
The thing is, let's go talk about this again. Because I
no,
have some.
this one is the easiest.
Yeah. There are like other approaches like using right, I'm left. But let's talk about this.
So this is the usual way, the simplest way.
Maybe it's, but do they have physical meaning or just?
No, strictly the good point of the matrix product states for physicists is that this is a strictly local way to write the quantum state. Well, this is important because if you have this, I cannot write it here. Let's go for it. I'm sorry, I'm taking the stage. So when you have this representation, I write much worse in the blackboard than Arturo. If you make any transformation, any physical transformation on the qubit ik, here the gate qubit will be made by identity everywhere in A-1, then unitary in the gate position, and then identities in the rest. here, what you have in general is that if you apply by to IK, you give something like L, LK, you another representation of the group, of the UD group, okay? LK, IK, LK, right? Then this part can be put into the matrix. And then this transformation only affects the K tensor of the problem. So it's explicitly local. This is the dedicated advantage.
Yeah, I had a question that Miguel just answered. I'm still thinking. Keep going.
Okay, any other thing regarding this?
Yeah, I think if you answer my question or not.
So the thing is that apart from MPS verifying this property of injectivity, we can also define injectivity for PEPs, which were the other ones I told you. The square lattice representation. And the good thing is that we now know that both MPS and PEPs, they can be related whenever they are injective using unitary transformations. That is a premiere. Because we didn't know that for PEPs.
Until now,
A few months ago.
I proved in my thesis is that it was Camila my very documented, and it has proven that it can be done by unit.
Yeah, so the idea for PEPs is the same, but for MPS, basically what we are doing is we are applying one here, one here, right? In the case of the past section, we were doing this, basically. And we knew that if this is A, it was equal to B, right? So the thing is that for PEPs, we didn't know that PEPs are a little bit more complicated. Since what? Too many? Chemist. Yeah, this is. Yeah, my third degree was in chemistry. And then for PEPs, it's quite different because you have these four legs, and then we already knew, and I don't know if you proved this, Nico, but we knew this, that we can do this to map one tensor, one PEP to the other one. We knew that this X, Y matrices, well not, they were from the, I'm going to use the mathematical notation for this, talking about that, but they are from the linear group. So they are invertible matrices. We knew that these matrices exist, but what we didn't know if whether or not these matrices X and Y could be living also on the unitary group. And that's what I proved. But I cannot tell you, sorry about that. I tell you the result, you can use it. So these ones are the ones that are useful. So the ones that you can find later. Any questions? So now we know that this can be transformed to this. Okay? So that means that now we know that all MPS are related by unitary transformations. All injective MPAs that generate the same state are related by unitary transformations, and the same applies for PEPs, which is cool. Not for you, but for physics. Okay, if you have any question, just let me know because I'm moving to a little bit of environment.
I have a question that maybe not it's
Okay.
around the activity of the group. At the beginning of your talk, you start saying that there is the space of all of the states that have the class, but there are only people that might be interested, and how is that related with MPS?
Okay, so MPS are the ones that can efficiently efficiently approximate this one. But for PEPs, we do know that they can map them directly. So this is what I was about to write before. So we know that if you take all the gamma states, PEPs are living here. What we know also is that we can approximate all of them up to a certain extent efficiently, which is cool. I put the epsilon just for the precision. So you have both.
You are missing one adjective there.
What?
What do you mean with efficient?
With the what?
What do you mean with efficient?
Oh, yeah. So,
Yeah.
polynomially. I mean polynomially. So you can calculate MPS, they sometimes grow with the number of particles, but for the gamma states, PEPs don't. They doesn't. Or if you take a certain PEP, you can find one that doesn't. They grow. They are polynomial with respect to the other ones, which is good. And the valuation itself is polynomial, which is quite good.
I think nobody has understood.
No.
I don't.
So the computation of the PEPs is itself.
No, because again, they can be
This thing.
So what I said before, the Carlos asked is when you can transform it, and I said you always can write any complex
Yeah.
as a metric database or as space, it doesn't matter. But the question behind is then how the size of the matrix grows when you are doing it.
Oh,
It grows exponentially. So the fundamental of the matrix is A that you are constructing this way is exponentially large. What the Arturo is saying that this efficient means that the size for this state, the size grows polynomial.
yeah. So if you want to calculate, you have a vector from the inverse space. This lives here. You need to provide all 2 to the n coefficients, right? But that's exponential with respect to the number of particles. If you have n particles, you have up to 2 to the n coefficients. With PEPs, you don't. So you just have to compute the whole infrastructure. And the thing is that to compute them, there are some efficient way to do it, and depends on the family of PEPs you're using, and the same applies for MPS. You can calculate them efficiently. Efficiently meaning that it's polynomial. So that doesn't depend on the number of particles exponentially, and sometimes it doesn't depend on the number of particles, which is quite good.
The notation of complexity states will have no entanglement. Because the whole dimension is the size of the matrix is exactly the dimension of the Smith prime.
What are you thinking?
Smith prime.
But can you represent every state with the PEPs?
Using approximation efficiently, more or less, yes.
Those are tricky
Yeah,
words.
only approximate.
Okay, so
What kind of approximation? Okay.
I'm not an expert in this matter, so take this with a pinch of salt. But as far as I know, all the gamma states they can be represented efficiently. No? Well, up to a certain epsilon.
No, that's because that is you are close to a phase transition externally with an efficiently in the sense with low dimension.
I do know that all gate Hamiltonians can be represented in a really cool, fancy way using.
So any state can be represented, but efficiently for us will be low dimension in the matrix.
Which means low entanglement.
It means
Low entanglement.
exactly. So
Okay.
if you are close to this transition, neither PEPs nor MPS are a good way to write it. You have to use metas.
So I apply this efficiently to quantum field theory. Because the vacuum of quantum field theory is higher than
For this one, we use the metas.
the what?
Meta.
Okay, this is
Scale, renormalization.
Ah, okay.
In this case, what you're using that everything is state environment. And then there is a special way to, or a special kind of test which is called meta.
Are there methods to calculate probability distributions from tensor networks which do not involve taking an exponential number of operations? Are there simplification methods to compute the probability distribution of a given tensor network, such that you need an exponential number of operations?
I do know that there are some results that can lead you to equivalent or to MPSs that are equivalent to other ones that are simpler to compute. If that's your question, yes, there are results for that, but they have to verify certain properties and certain conditions on the family of tensors. And yeah, it's. But when you say the probability, you mean the vector?
I mean, an actual physical thing you can measure.
Oh.
So that's, we have a tensor network, which it's a complex representation. You're using less parameters, less space to represent it, but we
Okay,
actually need to know the outcome. And we don't want to compute it with an exponential number of operations. So we could just simplify a tensor network graph.
Yes, you sometimes simplify the graph depending on the tensors you have, because depending on the properties they verify, you can sometimes, for example, you can take the minimum representation down. It's called the minimum representation form in English?
The capacity is called.
Oh, sorry. So there is something called, I think the translation is minimum representation form for MPS, which is kind of the canonical formula for all non-translational invariant thing, and then you can find the ones that are smaller than. Not the smallest in the sense of.
Yeah, because what I said there in the way we started with the singular variable position, the representation that you find is in general non-traditional environment. You have constructed to make it.
Yeah.
Even in the minimal.
There are some things that we are going over then without diving deep, but I don't want to go down that rabbit hole, because otherwise if we start wondering about why there's such an invariant, not there's such an invariant, then we'll have to draw the arrows and then have to do a space, and I don't want that. For the sake of you enjoying this. Okay.
Maybe it's already you can explain all the part of it, because I'm probably the only one interested in this.
Oh.
So, okay, then except if you want to continue.
I don't mind. If you want to know what the objective invariant theory, I'm not going to tell you any theorem or results, I'm just telling you what it is.
Can you do it in 5 minutes? Can you do it in 5 minutes?
In 5 minutes. Okay. So you mentioned invariant theory. It's just a theory that some guy called Manford made up, taking results from this old mathematician called Hilbert. So Hilbert was rattling off mathematicians with a lot of results. Manford found that some of them were very interesting. And he started to think about a certain problem that we usually have in mathematics. Probably you already know the Gaussian space. Please? You know what the Gaussian space is? Take up. Do you know what it is? Okay. So basically, if you have a vector space, and then you have a certain space with this vector space, you can take Gaussian space, which is basically identifying all the vectors living here under a equivalent relationship. Right?
Okay, this is the Gaussian space.
Yeah.
Okay.
It's what you want.
Is this for vector spaces? Yeah. Are we okay? Okay. So the thing is that in mathematics you keep creating this Gaussian space for a lot of different things. Sometimes you want to create relationship between elements, because you want to extract some important features and then make them a class, and then you create this quotient things to avoid having to deal with all the elements that shares which share this property. Okay, so the idea of geometric invariant theory is, okay, I want to create this B by W spaces, but I don't want them to lose the geometric properties they do have. So, to summarize it all, Mumford basically proves that there are some ways to build these quotient spaces by preserving the geometric properties they did have in the past. So that's the cool thing about geometric invariant theory. You are preserving
Geometric, what do you mean?
geometric properties.
Yeah, in the sense.
In the sense of geometry of
geometry.
orthogonality, angles, all those things, curvature, all those cool things that we have in mathematics. Mostly, we are also dealing here with what is called differential geometry, all those things. Mainly, you want to preserve all of the properties of, for example, when you have Euclidean manifolds, Euclidean spaces, they are quite vast study, and we already know a lot about them. But then you have Riemannian manifolds, and sometimes things can get a lot tricky there. So you want to preserve some properties, and that's why we use JIT. So JIT is basically a way of building things like quotient spaces gracefully, without breaking things in geometry. In this way, you can this can lead us to optimization using convex optimization, geodesically convex optimization, and all those things that are related to the geometry of the manifold. Otherwise, you cannot do it. That's why it is so. But I'm not diving deep into the Mumford theory for the sake of your mental health.
Okay.
Yeah, you can have any questions.
I have a silly question.
No, they are silly questions.
If we work in the Hilbert space, then we are in the Euclidean manifold and everything works fine. So.
No, because not everything works fine. So you are using, but depending on the schema you're using to approach the generation of the state, you are dealing with whether or not a general linear group or a unitary group, and under those groups, things can get a little bit messy. It's not that easy, so it's not just that you will have everything working as expected. As you told me, you cannot, for example, find the solutions of certain things to find the coefficients and then find that the manifold is convex. It is not. So most of the time, it is not convex. And this means that the underlying group is indeed not commutative. This again can be related to the geometric invariant theory, and then as it is not commutative, you try to see, okay, the group underlying, the group structure is underlying these things, not commutative, so I cannot use any linear programming tool. What can I use? I can try to force it to follow certain geometrical rules, and then try to apply geodesic optimization, for example. So you know that the structure of the geodesics are kept. And that's cool, because if you maintain those properties, you can use them.
No.
But this is it.
No.
I'm over
No.
high level discussion.